Okay, so today we're going to do a little more work with the variation material that we talked about the other day. Today we're going to look at more specifics, not just the idea of as one thing goes up, the other thing goes up, or as one thing goes up, the other thing goes down, but actually being able to like write and use equations based on information that we have. So we talked about direct, inverse, and very briefly joint or combination variation the other day. Remember, the idea behind direct variation is that, again, as one thing goes up, the other thing goes up. So if, I don't know, what are some examples we looked at the other day? Completely blanking. Direct variation from the other day. As it's been more days since my last haircut, my hair gets longer. As one thing goes up, the other thing goes up. Number of speeding tickets, cost of insurance. As one thing goes up, the other thing goes up. Okay. And then inverse variation was this inverse relationship. As one thing goes up, the other thing goes down. So the speed you drive versus the time it takes you to get somewhere. If your speed is low, the time is a lot. If your speed is high, if you're driving fast, that time goes down. The outside temperature and how much clothing you need to wear. Today, we have like a fairly nice day, right? It was in the 40s when I left the house this morning, where usually in February it's pretty cold. It's going to get cold again. But today, like, I didn't need to make my son wear like a hat and gloves to stand at the bus stop because it was a nice day outside. When it's colder, you've got to like bundle up like that kid from A Christmas Story. Okay, so direct versus inverse variation. Ideas we've talked about. Now we're going to look at being able to use specific information to be able to create a formula and then use that formula. So for our first example, it says the frequency of a vibrating cable varies inversely. That tells me what type of variation I'm looking at. Varies inversely as its length. So what I'm going to do here is start by writing something super generic. Okay, the frequency varies inversely as its length. Okay, if you look up at the top here, here's where I'm getting this from. Direct variation will have something like y equals k times x. For inverse variation, y equals k over x. Okay, as this number gets big, this number would get small and vice versa. And then for joint variation, it would be something like y equals k, x, z, however many variables I had in there. Okay, and then for each of these, we're seeing k. K is what we call our constant of variation. So that's the rate at which these things are related. Okay, that's the way I can think of this. So here is the general thing that we have going on. We know these two things vary inversely, the frequency and the length. And then we get a more specific sort of matched set of information. So for a cable that is 3 feet long, so our L is 3, it vibrates at 175 cycles per second. Our F would be 175. These two things go together. Okay. I could almost think of them sort of like a point. Okay. If I thought of this as a function I could graph, this would be a point on that graph. So what I'm going to do is plug in the pieces of information that I know to find K, to find that constant. To find anything else, I need to know that constant. So that's what I want to do next. So I know that 175 equals K over 3. And then I'm just going to solve for K here. Right now, I'm dividing by 3. I want to undo that. So we'll multiply by 3. So I would get K equals 525. 175 times 3 is 525. And then right at the very end here, I'm going to give my little formula with my K value plugged in. So F equals 525 over L. I can use that now for any other bits of information I want to figure out. I mentioned a minute ago that we could almost think of this like a point if we thought of this as a function to graph. So I'm actually going to pull up the graph on my calculator here for a second. This is zoomed way out. As you can see, this first tick mark's at 2000. But this is what my function would look like. Notice I have a vertical asymptote here, right? These are rational functions, like what we've talked about in our rational functions unit. It should make sense I have a vertical asymptote at 0, because if I were to plug 0 in for x, my function would be undefined. So all the same stuff that we've learned about still applies here, okay? So I get, again, this little rational graph. And for the purposes of our problem, the context here is we're talking about the length of a cable and the frequency at which it vibrates. This section of our graph probably doesn't make a lot of sense in the context of our problem, right? It doesn't make sense to talk about negative cable length or negative frequencies. But positive cable length and positive frequencies do make sense. So if we focus in on this section of the graph here in the first quadrant, what I want you to notice is that when our x values are really small, our y values are really big. And then as our x values get bigger, the y values get smaller and smaller and smaller, okay? That's an inverse relationship. That's inverse variation. And that is maybe even a little easier to see if we pull up the table here. So again, the negative values don't make so much sense in the context of our problem. There we can see undefined at 0 because we have an asymptote there. And then as I look at these positive values, as x gets bigger, y gets smaller. That's an inverse relationship. Okay, so we see an inverse relationship there. So then the next thing I want to look at is an answer to the question that it's asking me. It gave all this information and I kind of stopped it there, but there's a question at the end here. It says find the frequency of a 5-foot cable. So I know that the length of the cable is 5. I want to find the frequency of that cable. So I'm going to plug in my cable length to my little equation I've written to find the frequency. So 525 divided by 5, that'd be 105. And then anytime we have a context, we need to include the label. And our label for frequency is cycles per second. So again, this is an example of inverse variation. As one thing goes up, the other thing comes down. Questions for me so far? At the bottom of our page, we've got another example here, another variation example. For example 2, it says disregarding wind resistance, the distance a body falls from rest varies directly. So we've got some direct variation here, varies directly as the square of the time it falls. Got to be careful with that one, square of the time. So here's what I know. The distance varies directly. So this would be k times t. And it says the square of the time, so I got to square the time. I know direct variation. I'm going to hop up to the top for just a second. Should look like y equals my constant times x times that other variable. So that's what I've got here. And in this case, slight modification because again, it says varies directly as the square of the time. So I have to square the time.
Will we have to memorize these equations?
Nope. Okay, so that's the sort of general setup for what we have happening. Now, again, we get a specific piece of information. It says if a skydiver falls 64 feet in 2 seconds, so I get an x and a y that go together, or a d and a t that go together. So I'm going to plug these in. This is the distance, right? And this is a time. So I'm going to plug those in for their respective pieces in my little formula here. So 64 equals k times 2. And remember, I have to square it. So what I get here is 64 equals k times 4. I need to find that constant because again, that gives me that specific relationship, that ratio of how they're related. So I'm going to divide both sides by 4 and we get k to be 16. Now to have an equation that I can actually use to answer that question that they asked me, I want to take that k value and plug it in to my my general little equation here. So d equals 16 t squared. So we get a little quadratic here. Again, I want to hop to the graph really quickly. Now, we recognize this function as a quadratic. That t squared gives it away. So when I hop to the graph, I shouldn't be shocked, right? 16x squared in this case, right? If I use t, remember my calculator won't know what I'm talking about. Use x and y. I shouldn't be shocked that I see a little parabola here, right? Skinny parabola, okay? Again, for the context of our problem, the stuff in the second quadrant doesn't make a ton of sense. This would be falling for a negative amount of time. Probably doesn't make sense in the context of our problem since we're starting with a body at rest, it says. But everything in the first quadrant here, we can see as our x values get bigger, so do our y values, lots and lots bigger. And if I pull up the table, I can see, again, as my x values get bigger, my y values are also getting bigger. And now the last step of our problem here is to go ahead and actually answer the question that they've posed. So their question is, how far will he fall in 10 seconds? Okay, we have this information from our skydiver after 2 seconds. So how far will he have fallen after 10 seconds? So my question is based around a t value, right? A t of 10 seconds. So I'm just going to plug that in for t here. So 16 times 10 squared. Make sure you follow order of operations here. So I need to square first. This would be 100. So 16 times 100 gives me 1,600. And I think we're in feet. So that's how far he's fallen. Question for me so far. If I had a joint variation problem, which we don't see here on page 19, but if I had a joint variation problem, okay, I would set it up, it would say something like, let's say it was our skydiver problem. Let's say it says the distance that we fall varies directly as the square of the time and something else, okay? Then we would have d equals k times t squared times whatever that other variable is. And in order to solve for k, they would give me 3 pieces of information. Does that make sense? We'd have 3 things to plug in so that we could find k. Okay. What I would like you to do now is turn to page 21. And I would like you to take a look at problems 1 through 4 on page 21. 1 through 4 on page 21.